first problem, which gives us, says here the solubility, and it gives us a capital M, so that means we got molar solubility there. Now, molar solubility makes the problem easier to work. Okay? First thing we're going to do is we're going to take the COOH2, and we're going to write an equation for the dissolving of it. So we're going to take COOH2, that's a solid, and we're going to produce cobalt, aqueous, and 2 OH negatives, aqueous. Okay? Double L. We want to find KSP. KSP is the ion product. So KSP is going to be concentration of the CO plus 2 times the concentration of the OH negative squared. Okay? Now, according to the problem, it says the molar solubility is 3.7 times 10 to the minus 6. So that means that here, this will break down. Okay? Here it's going to give us the same value. That's how much dissolves. Here, since there's a 2 in front, we're going to get twice that value. So I'm going to take 6.7 times, 3.7 rather, 3.7 exponent minus 6 times 2. There's going to be 7.4 times 10 to the minus 6. Okay. Again, what did I do? This breaks down. Since there's a 1 here, I get the same amount. Since there's a 2 here, I get twice that amount. Now I put my numbers in here. KSP equals 3.7 times 10 to the minus 6 times 7.4 times 10 to the minus 6 squared. Okay? 3.7 exponent negative 6 times 7.4 exponent negative 6 squared. And that comes out to about 2.03 times 10 to the negative 16th. And that's my KSP. Okay? All right, second one. Now we want to know the grams per liter. We're given lead sulfate, and we're given a KSP of 1.6 times 10 to the negative 8. That's the KSP. So let's write the equation for the solution, the equation for the dissolving, and see what comes up. We're going to take PbSO4. That's going to give us Pb and SO4. Okay, lead sulfur. Right? KSP will equal concentration of the Pb times the concentration of the SO4. Okay? All right. If, just like we did with the other equation there, but this time we don't know amounts, so if we don't know amounts, we're just going to put an X in there. If I dissolve this amount of material, I'm going to get this amount of this ion, that amount of that ion. Everything's a 1-to-1 ratio, right? So now I can put values in and see what I come up with. I got a KSP. The KSP is 1.6 times 10 to the negative 8. That's going to equal x times x, or x squared. So x is going to be the square root of that. Square root of 1.6 exponent negative 8 is about 1.26 times 10 to the negative 4. Okay, follow carefully now. That is molar solubility. Okay? This value that I get here, the 1.26 times 10 to the negative 4th, is molar solubility. And remember from the beginning of the course, M is moles per liter. Okay? So what I want to do now is I want to take the moles per liter and I want to change it according to this to grams per liter. How am I going to do that? I'm going to change moles to grams, in other words.
You have to get the molecular weight.
Got to get the molecular weight, right? I got to multiply by the molecular weight. So I'm going to take lead, sulfur, 4 oxygens. Lead is 207. Sulfur is 32. 4 oxygens would be 64. Go back to the beginnings of the course here. Okay, and what do I get here? 7, 9, and 4 is 13, right? 10, 303. Okay? And that's grams per mole. So if I take this, multiply it by this, I come up with 0.0383 grams per liter, which is what they're asking. Okay, to change moles to liters to grams per liter, I multiply by the molecular weight. Now, what if I wanted grams per 100 milliliters? What would I do? Divide by what? Grams per 100 milliliters.
500.
Not by 100, no. I divide by 10. Okay, because 100 milliliters is 1/10 of a liter. Right? If I wanted grams per milliliter, I divide by 1,000, right? For every milliliter, I divide that by 1,000. So if I wanted the grams per milliliter, I take that divided by 1,000, get 0.00383. And then if I wanted something like 400 or 600 or 700 milliliters, I'd multiply by 400, 600, or 700, come up with my answer. Okay, when you're working with the problem, you're always working with moles per liter. Or grams per liter. Then you have to make corrections as you go along. All right. At any rate, number 10. We want to know if we mix equal volumes of